full view. So we're very happy to have here distinguished guests, and above all, our speaker today, who is very well known in our community, who has done a lot of work on the lunar ranging. He will talk us about it, and exciting news that are coming these days with new technologies, working at INFN Frascati. He has been till very recently representative of Italy in the United States from the on science matters. I cannot translate it. I think I'm translating more or less correctly your role. Yes, science attaché. And he just comes back with also a lot of discussions on technology with the American colleagues. So we were very happy to listen to that. I'm also very happy to listen to that because, as I told to some people, the lunar surface laser ranging, there are new papers coming out that show that could have impact or could measure with this exactly as you propose it. We could measure gravitational waves at the microhertz level as they come down to smaller frequencies. And there are ideas, of course, about sort of lunar strain meters that could use the technology. This is another issue. So without further ado, I hear.
Okay, it's a pleasure to be here and in the temple of gravitational physics. You do great things, so it's a pleasure for me to try and contribute. I was asked by Stavros to give a seminar on what physics we can do with the lunar ranging and how this can be useful also to start thinking of detecting potentially gravitational waves on the moon with the moon. Of course, I'm not an expert at all in gravitational waves, you are. So I'm here to describe a potential instrument which can be useful to do this study detection on the moon. So when you read there LLR, that means lunar laser ranging, where the stations are laser stations on Earth. Instead, lunar surface laser ranging is when you have a laser on the surface of the moon, and you have mirrors on the surface of the moon, which you try to do with one arm in the beginning, and then maybe two arms in the future, the usual job that you do with your interferometers. Of course, the environment is different, everything is more difficult, but there are many, many missions going to the moon. This is an opportunity. And anyway, I was contacted by Stavros and others. I was following their work in their proposal for detecting gravitational waves on the moon, and we think we are capable of providing an instrument for this. So that's why I started working on this with Stavros and others in Europe. You see there a list of people from Frascati, and then we're working with three agencies, Italian Space Agency, European Space Agency, and NASA, with historical partners at University of Maryland. There is an Apollo veteran who did the reflectors for the Apollo missions back in the late 60s and is still active today, 85 plus years old. So we developed together the core idea of an instrument to do lunar laser ranging. Now, you will see later another author list, which is the people working with Stavros on the lunar seismic and gravitational antenna. So I will not talk only about probing general relativity in weak field slow motion, which is what we do with the standard lunar laser ranging. I will also try to see to show you how the instrument can be useful for detecting gravitational waves. I will not talk about the gravitational wave physics. You know it better than me. You don't need me to explain that. There are specific reasons to go to the moon in a certain range of frequency. But I will describe the instrumentation. Okay, so the first part will be about weak field slow motion physics. Okay, that has been done in the last 5 decades using the Apollo and Lunar code reflectors on the moon. So I will go into some of these measurements, beta, weak and strong equivalence principle, etc. And then the lunar surface missions, which are very imminent, 23, 24. And then in the second part, I will explain how this reflector system can be evolved and adapted, optimized for the proposal that Stavros and others have been putting together, the lunar seismic and gravitational antenna. In fact, I will take a few slides from Stavros that he used for a recent proposal and highlight the relevance of reflectors. We call this reflector Moonlight. You will see the acronym later. It's funded by committee number 2 within INFN. And then we are building the pointing actuators in order to point the reflector to Earth or to a laser on the surface of the moon under ESA. And we are also building a robotic dust cover to prevent the accumulation of regolith on the face of the reflector, which would be, of course, a problem. You don't want your gravitational mirror to be covered with dust. The first opportunity to deploy this system will be in 2024, using the NASA framework, and ESA signed a dedicated MOU with NASA in early 2022. So this slide here shows the menu of reflectors that we are building in Italy with ASI. So you see at the top right corner the lunar reflector. So the glass there has a diameter of 10 centimeters. And next to that, you see a drawing with the pointing actuators for elevation and azimuth. We made small reflectors that can stay in the palm of a hand for Mars and Phobos missions. We are flying those. We have flown those already. At the bottom, you see a big array of reflectors that has a diameter of 35 centimeters. We are under contract with Thales and Airbus to provide those kind of flat array reflectors for Galileo second generation. And then on the bottom left corner, you see a spherical cap called Legios, which is a spherical satellite, a cannonball satellite. It's the realization of what we study in the first physics course, the point of the material point of mass m. Okay, so that's the best approximation we can do in classical physics in space. It's a sphere with a diameter of 40 centimeters. It's called LARES-2. It will be launched this summer. Its shape and mass is well controlled, and it's filled with the reflectors on the surface. You measure the time of flight. So you actually measure the three-dimensional vector between the laser station and the point of mass m in space. These are other pictures of this new satellite called LARES-2. So we built it for ASI. It was built, the mechanics was done by INFN Padua, and the rest of it, the qualifications, the test of the reflectors, the mounting, the integration of the reflectors on the sphere, 303 reflectors, was done in Frascati. It's 303 reflectors, the diameter is 40 centimeters, and the weight is 300 kilograms. It will go on the first qualification flight of the Vega C, the small rocket that ESA is inaugurating this year, this summer. You see there the mass, the test mass on a separation system made by OHB Milan, and that on the Vega. Now, you see here the main instrument. It's a reflector with a diameter of 10 centimeters. You see it next to the ExoMars microreflector. The difference between the two is that the big reflector is measured with stations on Earth. Côte d'Azur, the French one, Matera in Italy. The other one, the small reflector, is measured with the orbiting lasers, which are orbiting either Mars or the Moon. And then we have two facilities in Frascati where we basically do the test of the performance of the reflectors in space conditions. We don't just do the TVT, the thermal vacuum testing. We also induce the perturbation of the sun heat on the reflectors. This is exposed optics. There is no obturator, so they see the light, the laser light coming from the Earth, but also the sunlight. So they're peculiar mirrors, non-sequential surfaces, and they have to be designed with a passive thermal control such that they perform okay on Galileo, in orbit around the Earth, or on the Moon. That's our job. So we do a sort of test beam of laser reflectors. We put them in the space conditions, vacuum, cold, sun illumination, and then we rotate them like if they were in orbit, and then we measure from an external optical circuit the laser far field diffraction patterns. That is how much light comes back to the ground stations. Okay, so this is the menu of weak field slow motion measurements that have been done in the last 50 years using the reflectors now on the moon, 3 Apollo, 11, 14, and 15, plus your lunar code 1 and 2. So you see the classical measurements of the weak equivalence principle, the strong equivalence principle, related to that through the eta parameter of Northbet, you can measure beta -1, and then G dot over G. And then you can also measure the geodetic precession, which is a three-body effect. The moon rotating around the Earth is like an angular momentum spin, and that precesses, the direction of the spin precesses when it orbits a central gravitational well like the Sun. And then we also test deviations from the inverse square law in the form of Yukawa potential. And the next slides are meant to show you a little bit the physics underneath. Of course, it's classical physics, so we'll not go too much into the detail, but I want to give you a flavor of how you can do these measurements in a small closed system, taking advantage that the relative position between the Earth and the Moon is measured with a very, very high accuracy of the order of few centimeters, and with the new reflectors down to millimeter. And it's a closed system which does many orbits, so the statistics accumulates very, very fast. So let's start from the equivalence principle. So by looking at the relative acceleration between the Earth and the Moon, we can measure their different acceleration in the field of the Sun. So it's a classical Galileo experiment. You have two bodies, one orbiting the other, but they both fall in the field of the Sun. So we can measure any difference in those ratios of the masses. Of course, there is gravitational mass and the inertial mass. And once you clean the data, you can get to a measurement which is of the order of 10 to the minus 13. So what happens is that if the weak equivalence principle is violated, then the lunar orbit is displaced with respect to the Earth orbit. So the lunar orbit, on average, should be the Earth orbit, because seen from the Sun, the Earth is orbiting around the Earth. But the orbit of the Moon with respect to the Sun is like that, okay, along the orbit of the Earth. However, if the average position of this wobbling lunar orbit is not the center of mass of the Earth, it means that there is a relative acceleration, because the two quality of masses are different. Earth has a metal core, the Moon doesn't. So it's like you compare, a piece of metal and a brick. So if there is a violation of the equivalence principle, then you should see a displacement. Now, because the measurements are very precise, you can do this job and you can get to 10 to the minus 13. And that's the equivalence principle. Now, the test we do with the Earth and the Moon is sensitive both to composition-dependent violations, which is what Galileo was, of course, testing, but also to self-energy violations. So to violations related to the quantity of mass, not the quality of mass. You can picture the famous experiment of the astronaut on the Moon having the hammer and the feather, which were falling with the same acceleration, more or less. So what we can do with the Moon and the Earth falling in the field of the Sun is an experiment like that, but with a big hammer and a small hammer, in which you test really if there is a violation related to the quantity of mass. In order to do this, you need astronomical bodies. So you cannot tell two stars in the sky to do this experiment for you, because you cannot measure the relative position of two stars in the sky. The only place in the solar system where you can have a laboratory in which you can go with missions and put the sensors and make this relative acceleration is the Moon. In principle, if we put reflectors on Mars or Mercury, we could do a similar experiment. But doing two-way laser ranging to Mars cannot be done, because you would need a tennis court full of reflectors, which is not feasible. Similarly for Mercury. So the only place where we can do easily this, relatively easily, this experiment with astronomical masses and test big hammer versus small hammer is the Earth Moon. So if you do the mathematics, you use the equations as usual, and you subtract. You subtract the violation due to the composition dependence from what you measure from laser ranging, then you're left with the strong potential strong violation. So what you do, you measure on the ground with the experiments with the torsion balances of the University of Washington in United States. They have torsion balances and they measure with different compositions of bodies. They measure the relative acceleration with respect to the sun. And they measure that there is no violation at the level of, you see there, weak equivalence principle, University of Washington, UW. You measure that number. So there is no violation below 1.4 10 to the minus 13. So it's a ground experiment, a lab experiment, a tabletop experiment. And you do that with the two replicas of the Earth and the Moon. So you use, they made a miniature Earth and a miniature Moon. Knowing the internal composition of the two bodies, they made a torsion balance in front of the sun with that composition. A very difficult but accurate experiment done several years ago. You see the years there, 1999 and 2001. Then they stopped doing the experiment because the accuracy they get is already at the level of the lunar laser ranging. Since you have to do subtraction, you don't need a very, very accurate lab experiment and a space experiment, which is of a different order of magnitude, because you have to subtract those. When you subtract those, you do square root of 2 more or less of the error, and then you end up with that measurement there, which is the lunar laser ranging equivalence principle subtracted by the weak equivalence principle measured on the ground, and you're left with a strong equivalence principle. That's a very good question. The solar mass, I don't remember, I don't know by heart, but they know they have a database of constants, which they have to keep under control. Yes, they also have to assume a value or use a value, a measured value for the quadruple of the sun. That's of interest for solar physics. So they're very known. They're called the Eötvös experiments, Adelberger and collaborators. Now, if we improve the lunar laser ranging measurements, then we should ask them to go back in the lab and improve their measurements, because then if we want to do this subtraction, you need to have errors of comparable entity. Anyway, if you use the known relationships between the ratio of masses and eta, the Nordtvedt parameter, then you go down, you get a limit on beta -1, which is of the order of 10 to the -4. Now, this is one of the best measurements. It's a measurement of a few years ago. So I reported this only to give a flavor of how you do the measurement. With the different missions now, we can have limits on beta, which are 10 to the -5. Now, in our case, if we can get new reflectors on the moon, and I will show you that we are getting new reflectors of the moon, we will improve the limit on beta from 10 to the -4 to 10 to the -6. So it's a factor of 10, up to a factor of 10 of improvement. In all the other variables there, we can get more or less an improvement of up to a factor of 100. Why? Because the accuracy of the reflectors now is a few centimeters, 2, 3, 4 centimeters. Now, we can go easily to 1 millimeter because the lasers are much better now than before, because the new reflectors are better. Then to go the other factor of 10, it's more difficult. That's the ultimate goal. And this is because you have to take into account at a higher accuracy the interior of the moon. You can make the point-like mass in the laboratory, like LARES, but the moon is a body which has tides, has an internal structure. The internal structure of the moon is pretty well known, but not completely. There are missions which only want to do that, improve the interior of the moon. At present level, we need a better knowledge of the interior of the moon with seismometers and geophysics missions in order to go from 1 millimeter to 0.1 millimeter. So we have the best instrument which supports out of the box 0.1 millimeter. So concerning the space segment, we're already there. The stations have improved, they will improve more, but to do the last step, from 1 millimeter to 0.1 millimeter, we also need the geophysics of the planet, of the body. So that's why, Stavros, we work so closely together with Philippe Lognonnet and all the other people who do seismometry. So seismometer and reflectors, already at the time of the Apollo missions, were very close tied together. The reflectors are very sensitive to the deep interior. They show that there is probably either a very small core, silicon core, solid, and then a molten layer, or that there is a liquid core. With the seismometry, you do a lot of the rest, from the deep core up to the crust. So the two instruments are very complementary. Yes.
So at that point, this is the rough model data for testing the limit on the passive and active mass. The difference between passive and active mass is an old measurement. So I wonder if there is some systematic effect due to the location of the instrument, because
yes, well, the model you're mentioning is not the one of the most sophisticated.
No, so that is old measurements, the first outcome of the Apollo missions.
Yes, so a lot of work has been done even in the reanalysis of those data. So there is a number of people, Philippe Lognonnet, René Weber, and many others working all over Europe and the US on seismometry to have a better model of the moon. Of course, one of the limitations, both of the seismometers and the reflectors, is that they were put by the Apollo missions in the central front part of the moon. Ideally, you want to have seismometers and reflectors north, south, east, west, or on the limb of the moon, okay? So there is a strong geographic limitation. There is nothing on the far side. So we need to go to the far side. Seismometers there are important. Reflectors, if you put them there, you can measure them from orbit. So yes, the geographical distribution is a key factor. But there are missions. The solution to this is that there are many missions now going to the moon.
Since we intervene during, yeah, there will be the far side mission, as you say. I mean, they will be already, the 24 will know much better, I think, the structure of the moon.
Yes, there will
but probably you will say it. If you say it, don't answer. I mean, your gain on the millimeter level already is because of the bigger mirror and collecting more photons.
No, the reason is the following. The Apollo mirrors, they have arrays of mirrors, so the physical finite size of 1 meter. So the moon librates by north, south, east, west by almost 10 degrees. So the sometimes you hit the reflector which is near, physically near. Sometimes you will get a return from the one which is far away. So if you do the histogram of the laser returns, you get a Gaussian which has a width of 2 nanoseconds. Okay, so you have 1,000 entries. You make the average value, the mean of the Gaussian with 2 centimeters, but you start with 60, and you waste at least 1,000 or more measurements. If you have a single reflector, it does move with the moon by up to 150 kilometers, but you can track that with your software. And even if the single reflector tilts, then it always retroreflects from the tip. So this Gaussian becomes a delta. So, and each measurement you get is one normal point, one physical observable instead of 1,000. So there is a huge gain in going from a single going from an array to a single reflector.
And no, this is where my question then is, because here we are supposedly experts in mirrors and big. I mean, would you, for instance, a much bigger mirror than 10 centimeters would gain you more, or you're at the limits of?
For local lunar, for surface lunar laser ranging, if you have a bigger mirror, you get more light, and the signal is increased, and there is no other effect. If you do a big mirror for standard lunar laser ranging, there you measure the time of flight and you exploit the diffraction. So if you increase the diameter, say to 50 centimeters, then your diffraction is very, very narrow because it goes as a lambda over the aperture. So you don't see a signal anymore because the central far-field diffraction pattern is very, very, very narrow. And at the angle where you get the light back, you have a little light. This is because it's a velocity aberration effect. If I do a laser range into Helena, then of course I'm orbiting, or Helena is orbiting. So when the light comes back, if it comes back in the very same direction, I miss it because I moved elsewhere. So we use the natural broadening of the diffraction in order to get some of the light which comes back into my mirror. Now, this depends on the relative velocity between me and Helena. For the moon, this velocity aberration is very low because the moon is very far. It's 4.5 microradians. If I enlarge the mirror diameter, then all the laser return goes inside 1 or 2 microradians. So at 4 microradians, there is little left. So for lunar laser ranging, you want to have 10 centimeters, 11, 9, something like that. It kills you if you have 30 centimeters. But on the moon, of course, it's basically near field. So if that improves your SNR, then we can improve enlarge the diameter. Okay, so here there is a long reasoning of how we can test fundamental constants using the lunar laser ranging. Now, the G variation, in many models, it can be due to the expansion of the universe. There are many models. One model says that it's proportional to the Hubble constant with the sigma parameter, which depends on the specific cosmological model. This is motivated by superstring theories. There is a lot of physics underneath that, behind that. Now, because the system is closed, even though the size of the system, the radius is very small, 1/3 of a million kilometers, but because you measure this distance, this is my major axis of the orbit, very, very accurately at centimeter level for many orbits for 50 years, then you do an error, you get an error which allows you to test, you see there, 10 to the minus 13 per year. And you can improve that linearly with your improved accuracy. So if you improve the accuracy by a factor of 10, you improve a factor of 10 there. If you improve by a factor of 20 or so, or 100, then you improve the limit down to 10 to the minus 15, which is a good measurement. I'm not considering that. Not at all. Not at all.
And this is where I would like to tell you that there was, on the 1st of April, there was an article that said that you could, probably I sent you the reference.
Yes.
That you could test, between the Hubble tension, you could measure it very precisely, exactly with this technique.
So you're telling me
it was the 1st of April article. I didn't believe it, but we have to read it carefully. I think it's very interesting.
You measure, if you assume that G dot is 0, then you can test something else. Of course, now, this is a very deep question. We are doing the same, we are trying to do the same measurements at the least of G dot and beta using Mars. Okay. Now, we can put reflectors on Mars, measure their position accurately from orbit, and then measure the position of the orbiter. Okay. So the radio science for orbiters is very good. You will see that the Bepi-Colombo mission has a very good radio science and can do radar ranging at the meter level. Okay, laser ranging goes down to millimeter, but that's a different wavelength. But meter level for Mercury or Mars, then it means you can measure the ephemerides very, very accurately, and you can, in principle, measure. Not in principle, you can measure beta and G dot also with Mars. Now, in the case of Mars, the beta is a three-body effect, which is Jupiter, Mars, Sun. For the Earth and the Moon is Sun, Earth, Moon. And there are different measurements with completely different systematic errors. Very short baseline of laser for Mars and very long for the Earth. You have the radar ranging, which is more robust in other respects. And Italy, Thales Alenia, is very, very good at doing radio science. So the answer is we can measure a potential deviation with two different planetary systems. And that gives you increased confidence that you are measuring something. for real. And then you can have more measurements to disentangle where the violation or the deviation comes from. But with a single system, with a single measurement, you're right. You don't know. If you measure a violation of the equivalence principle with the moon, then you don't know in principle immediately if it's weak or strong. You need a better or equivalent ground experiment, which can be done because it's tabletop. Adelberger will not live forever, but I mean, his group will keep doing the experiment. So if we have a deviation, then we push the theorists. We now are pushing the stations to improve their lasers. Before they didn't have any reason to improve their lasers because the limitation was the space segment, the 2 nanosecond Gaussian. Now that becomes a delta with the new reflectors.
Question. No, I am interested in these numbers for a reason that I will explain later. But, no, I have another number which is slightly better, which was obtained from a global fit performed on orbits of planets and satellites that is in the range of 10 to minus 14. So I wonder that this number with the lunar laser engine can be improved or not.
Yes, it can be improved if we go back to the table. Once we have new reflectors on the moon, then G dot over G will go down to 5 10 to the minus 14. And then if
and
the
then
geophysics,
5 10 to minus 14
yes.
and 5 10 to minus 15.
Yes.
That is interesting. Yes, okay, thank you.
then the moon being a non-trivial body, non-isotropic, non-homogeneous, then in order to go the next factor 10, you need the geophysics. So, and what Stavros is proposing is to do gravitational physics with seismometers, for example, with reflectors. So all those nodes, missions will improve the knowledge of the interior of the moon, which is needed for many reasons. Okay, then there is the classic measurement of the geodetic precession, and the amount of precession is 3 meters per orbit. So every 28 days, the perigee of the moon moves by 3 meters. And that increases and sums up every 28 days. So it's a lot of kilometers of precession that the moon has done in the last 50 years. So we measure that with, at the moment, a few centimeter accuracy. And so the original measurement by Shapiro was 2 seconds per century in 1988. And then since then, we are improving with statistics and with time this number. Okay, so it's a classic measurement of general relativity, but it's correlated with the interior of the moon. See, you see the love numbers, which describe the lunar oblateness of the interior. There is an uncertainty on those, so that goes into your estimate of the KGP. However, recently there were orbital missions like GRACE, not GRACE, GRAIL, gravity recovery and interior experiment. What was the other one? LRO, the Lunar Reconnaissance Orbiter, which has measured the shape with the laser altimetry. So by coupling gravity measurements with shape and distance measurement on a global scale, NASA has been able to improve the knowledge of the interior of the moon. Now, of course, if you put the seismometers on the surface, that helps very, very, very much, and also reflectors. But already with the past decade, 2009, 2005, 2015, a lot of lunar missions, not only by NASA, but also Selene 2 by Japan, Chang'e 1, Chang'e 2, Chang'e 3 by CNSA, China, Smart 1 mission by ESA even before. So the interior and the gravitational model, the spherical harmonics functions of the moon have improved quite a bit. Now that we go on the surface, things will speed up considerably. Okay, so let me go forward. Let me skip this test of Lorentz violation with laser ranging because I have a lot of material and I want to get also to what can be useful for gravitational waves. This is a classic measurement of the inverse square law deviations in the solar system. You have seen this plot before, perhaps. So it's alpha. So it's a Yukawa potential, alpha times the Newtonian gravity, and then with the exponent, Yukawa exponent with the lambda range. So in this plot, you have a lambda on the horizontal axis and alpha on the vertical axis. So with the satellites, with the lunar laser engine and satellite laser engine, you see there LLR, lunar laser engine, at the value 6 in the powers of alpha. So that's the Earth-Moon distance, 1/3 of a million kilometers. So there, sorry, close to 9. That's the tip of the green excluded region. So at the moment we are around alpha 10 to the minus 10 or several 10 to the minus 11. Again, with the new reflectors, we can do an improvement of a factor of 10. It's pure scaling of metric meaning the distance. And then with the improvement of geophysics, we can go up to a factor 100. Of course, this game of alpha versus lambda is done also in different regions of the solar system and on the laboratory. The laboratory measurements there, the light blue that you see, alpha 10 to the minus 1, minus 2, minus 3, those have been done by Adelberger and collaborators at the University of Washington. They do measurements with small bodies at close distances, down to 100 microns or less, and they have to do that in vacuum. So it's a very delicate tabletop experiment, and if you put rotating wheels with different materials in order to test the inverse square law there, the difficulty is that in vacuum, when they get too close, they stick to each other. So you have to do a very accurate setup in order to be able to go to the 100 microns. And of course, there the uncertainty is very large. And then there are the planetary experiments. There was one deep space gravity probe proposed by JPL many years ago in order to go in the outer part of the solar system in order to test or verify the so-called pioneer anomaly. Okay, but the best measurements you do in a closed system, Earth and Moon, because there you have the best accuracy, orbits repeat very frequently, and you have more statistics. Now there is a list of slides now to tell you how we can measure positions with lasers, the Moon, and with the radar engine, Mercury, and put constraints on theories beyond general relativity. One of them, what those is a space-time torsion. Okay, so it's a long list of slides. I will only touch a few of those to give you a flavor, and I will leave them in the slides in the presentation as a reference. Now, a few years ago, 2007, the group Alan Guth, the inventor of inflation, made a theory of space-time torsion with those collaborators, and they did that in order to test this prediction using Gravity Probe B. Gravity Probe B is an experiment of NASA in which they have a superconducting sphere which rotates in space in a drag-free satellite, and they wanted to test the frame dragging, the line steering effect of this spin artificially made inside a drag-free satellite like LISA, for example, and see if that moving in the field of the Earth would tilt its axis because of the dragging of the inertial flames done by Earth. Okay, do that measurement with the Largest Solaris, the dragging of inertial flames, or you can do it also not with an orbital angular momentum, but with a spin. Okay, so in principle, if there is a field of space-time torsion, so space-time torsion which is not generated by particles carrying spin, like there is a theory which predicts that if the graviton, the supersymmetric pattern of the graviton could make torsion in space-time, and it makes it because there are particles which carry this torsion. This theory is instead a classical theory, no particles. It says, let's assume that Einstein forgot space-time torsion, and that in addition to space-time curvature, there is also space-time torsion. Of course, Einstein didn't forget that. He did the first models. He also put mathematically space-time torsion. The fact is that nature didn't choose to have also space-time torsion together with the space-time curvature. So Einstein abandoned this idea. He made a model, but the model was grossly not verified by measurements, so he threw it away. Many years later, they did this model. They made this assumption. So there are trajectories which are not geodesics, but they are teleparallel trajectories in which the way a body moves takes into account curvature, but also distortion. Okay. Now, to cut a long story short, they made up a model which had several parameters. So these parameters in the theory were of space-time torsion. In addition to general relativity, there is T1, T2, and T3, which are dimensionless parameters which give additional precessions of the Moon and Mercury. And then there are additional frame dragging parameters. So in addition to the classic land steering frame dragging, there would be another source given by those 5 parameters. Okay, so now nature didn't choose so. All the limits indicate that there is no space-time torsion, but this is an example of a theory which can be tested by a combination of experiments using lasers, using radars, and using a satellite with a perfect spinning particle. Now, so I will go quickly to this in order to show you that if you go, for example, in the plane 1 minus beta plus T3, one of the parameters which describes the precessions, the secular effects, then you can put a limit on this combination 1 minus beta plus T3 and on T2 by using, you see the constraint at the bottom and the top of lunar laser ranging and Mercury radar ranging, okay? And in the future, other experiments like Bepi Colombo. And then you have a limit, the shaded area, which comes from the measurement of the geodetic precession, which can be done, which is done by lunar laser ranging and gravity probe B. So at the moment, the measurement of the geodetic precession is at 6 per mil level with lunar laser ranging. The accuracy on beta minus 1 at the time was 1 per mil. It is improving now. And then you can do other measurements of T3 and T2 using radar data and lunar laser ranging data, and you can put this together. So in this plot here, you see the improved measurement of the geodetic precession by gravity probe B a few years ago. So they narrowed the region which was measured before by lunar geodetic precession. So their accuracy in the end was about 3 per mil. But GPB is finished, so they will never improve anymore. With reflectors in the future, we can also improve and go in a plane of new physics like this to play this game. And the game goes on and on. In the future, Bepi Colombo, well, in the near future, Bepi Colombo has been launched. 2 orbiters, which will be measured with radio science by Thales Alenia, which is very accurate. So it's a kind of measurement in which you put together radar ranging, lunar laser ranging, theory, and then you can do improvements also using the spherical satellites, LEGIOS and LARES, because with the LEGIOS and LARES, you do measure the frame dragging. You see there that the GPB measures that combination. LEGIOS and LARES, they measure a different combination, okay? So this is to tell you satellite laser ranging, lunar laser ranging have a good potential and can measure different effects, really different kinds of physics. So this is the end of the story. The 2 experiments have different sensitivities, but they have also different systematic effects. So if you see a signal with both, that's a good thing because it means it's not likely that you make wrong 2 experiments. Anyway, so I will leave this as a reference in the slide. The future potential improvement in this kind of physics searches for space-time torsion or, for example, non-minimally coupled with gravity can be done with improvements in the measurements. Now we have in front of us with the reflectors a factor of 10, potentially more, up to 100 the improvement. Bepi Colombo will reach Mercury and will do a better measurement of the perihelion advance using, of course, so measuring beta much better, and also gamma. Gamma now is fixed at the value of Cassini, 2.5 10 to minus 5, but with baby Colombo, that could improve by 1 or 2 orders of magnitude. Okay, so finish with the weak field slow motion. Let me show you the instrument and then see how this can be useful also for gravitational waves on the moon. So we have a reflector with a 10 centimeter diameter, then we have pointing actuators. Now these are needed in order to make sure that if the lander lands with the wrong azimuth by 30 degrees, then since the field of view of the reflector is 20 degrees, then you don't see a return, okay? So you need to have something which corrects for that and corrects for tilt, local tilt in the slopes of the terrain. Now, there are very good maps, so you know that we are landing in a place where the slope is, say, 2 degrees or 1 degree. You choose that spot and you go there. However, there can be a problem. We have seen that the last 2 landers on the moon crash. Chandrayaan-2 crashed, it was really tilted like this. Apollo 17 was tilted by 30 degrees. If you look at the pictures of Apollo 16, they're impressive. It's really tilted by 32 degrees, like this. The commercial Israeli lander crashed completely. Now, the new missions are funded by NASA, by ESA, so they will be better. But this kind of pointing is useful. Now, for the gravitational wave experiment, you need this pointing because you cannot align the mirrors like you do in Virgo. So you want to use a retroreflector, the fact that it retroreflects and within 1 or 2 degrees, you don't have to take care of anything. You need to have it stable, good optical quality, good coatings, which take into account the thermal environment of the moon, but you need the reflectors, so you need to be able to point. And then Stavros' idea and my idea is to make redundancy in the system in order to do both weak field slow motion physics with the Earth lasers and local lunar laser ranging for gravitational waves. So we do need this point in the accuracy for that specific instrument. So the total mass is 4 kilograms, about 650 grams are the glass. You feel it in your hand. The glass is very light, but this one, you feel it in your hand. Usual slew of materials and interfaces and coatings. These are coatings and things that are foreseen for thermal control, passive thermal control, because then the electronics will die of the mission after 14 days. At the end of the lunar day, the mission dies. There are no nuclear power, no RTGs, so everything must be done in 14 days. And this is the quality of this reflector is a wave over 10, or wave over 8, wave over 4 total, which is a gross accuracy for your mirrors, but it's good enough for doing time of flight and diffraction limited physics. Of course, this piece of optics can be done much better. If you spend more money, you can have the surface is good at lambda wave over 30 or more, and then there are the coatings. But then you have to take into account the thermal environment. So you're not in vacuum. Well, you are in vacuum, but you're not in a thermally controlled environment. Okay, we have foreseen a cover in order to protect the face of the reflector from dust rays when the lander lands. Then the lander deploys in our mission 4 rovers, 5 rovers actually, 4 by JPL and another rover from another company. So they move 5 of them around, so there is dust. We don't want to open that before they finish the deploying. Then they go away. They do the stuff at several hundreds of kilometers away. The dust will settle. We are on a shelf at mid-height of the lander, which is like this. I've seen it in Houston. So the dust that we will get in the beginning will be very, very little. Then there is an accumulation of dust, which is low. We know the number. In 5 decades, the Apollo reflectors reduced their laser return by a factor of 10, which means a factor of 2 every 10 years. Now, if we do a Pathfinder experiment of your experiment, I think 10 years are enough, or even less, of course. So dust with this device, which avoids the spray of the dust in the beginning, will be very good. Of course, in Stavros' idea, there is deployment of there is a lander which lands, of course, and then you have to deploy the reflector and the seismometer far away. You have to deploy in his ideas also the fiber. So you do need mobility. And mobility is something which will be tested very soon with different solutions. Okay, so these are canonical. This is not new technology, but you have to do something not too heavy, not too light, robust enough that it resists after the 14 days of lunar day, and customize for a piece of optics, which is exactly a reflector of 10 centimeter or more diameter. Then if there are RTGs in the mission, of course, that's a different story, but that's an option now. Let me say that RTGs on the moon were not an option until Trump. One of the few things that Trump did that NASA liked was to restart the production of plutonium. So because that now the US, NASA is running Curiosity and Perseverance using Sovietic, not even Russian, Sovietic plutonium, okay? And when Trump heard that, said, we cannot do that. So at least it changed this thing. Okay, so the site where we are going is so-called the Reiner Gamma swirl because it's a really curly structure there. See? And it's a magnetic anomaly. So there is a residual magnetic field there. So when the solar wind comes, is swept away by the local non-zero magnetic field. So it doesn't weather, it doesn't age, deregulate like in the surroundings. So from the point of view of planetology, it's very, very interesting for them. So the lunar scientists really want to go there, do measurements. That's why there are rovers. One of the rovers is supposed to go there and understand, measure the magnetic field, and plus other geochemical measurements around the Earth. So it's apparently a very interesting lunar science site. The coordinates are very interesting. You see 58 degrees west. So it's almost all west. Now, take into account that you have to add to that 10 degrees of librations. So you don't want something at 80 degrees because then with librations, you don't see it. And the deployment at the very limb is non-trivial. So this is good for us. It's very far from the center where all the Apollo missions have been. Okay, so what is going on in terms of missions? Now, these are the next missions. Now, the first missions are Astrobotic, Lacus Mortis, top right. So that's a lander which goes to Lacus Mortis, and it's racing to be the first commercial mission on the moon, together with what is it? Intuitive Machines, IM-1, top left. The delivery site is Oceanos Procellarium. The provider is Intuitive Machines, a firm from Houston with which we work because they are the ones who make the lander. You see here, IM-3, Intuitive Machines 3 is a reflector, ours plus pointing plus task cover. Also for small rovers by JPL, the Cadre. So that goes to the Reiner Gamma. And then there is an Intuitive Machines number 2, which will fly by the end of 2022. So our mission is 2024. The first two missions, top left and right, are not the Q1 2022. You see it already. It's going to be Q3 or Q4. And we will see which one of them, Astrobotic or Intuitive Machines, will win the race. Anyway, on Intuitive Machines 2, this one rover by Lunar Outpost. And then that rover will host an INFN microreflector, a small one that we put on Mars. And that will be measured by the Lunar Reconnaissance Orbiter. Now, in addition to a rover, Stavros, there is a hopper on the mission. So we will see a hopper within a couple of years. Well, they say November 22, that will probably be beginning of 23. That goes to the pole. So they go there to, of course, test a drill in order to find the volatiles, the ice. And they will land near a shadowed crater, near PSR. Then the rover will start moving along the rim of the crater, doing several measurements with our reflector on top, so it can be monitored where it goes. And then the hopper will move later much quicker, because the hopper hops, and everything goes well. It can hop by a few hundred meters, take measurements, and then follow the rover without falling on top of each other, of course. So we will see this technology in action. I've put the abstract of the paper you found on this mission. So we are working with Intuitive Machines very, very closely for 2 missions. So we missed the flight on the first one, IM-1, because we didn't find the money to pay for one Moonlight fixed pointing. which was 1 kilogram. So NASA instead is flying a NASA reflector with fixed pointing. It's identical to ours. I mean, the idea of the reflector. But they didn't do a program to provide the reflector with the pointing actuators and dust cover. So that's without dust cover, without fixed pointing. They assume that the lander will run correctly. Okay, that's a mission going to Mare Crisium, and the lander will be by Firefly, another firm. So you see here different names of firms. Masten will go to the South Pole, Astrobotic, Intuitive Machines, Firefly. Another which was very popular was Moon Express, which didn't make it to the first selection. Deep Space Systems will get one mission. Lockheed Martin got into a race, but they told Lockheed Martin, you cannot ask for 400 millions and say you make a lander which works 100%. The budget here for each mission is between 80 and 90 millions of dollars. Okay, so Lockheed Martin in the beginning didn't care. But there are many missions, and most of these missions are full up to 2025. The payload, so the mission is paid by NASA, 90 millions, and then there is typically 30 kilograms of payload or more. NASA is getting half of that or a fraction of that, and it selects by itself internal NASA payloads or US payloads. And then a large fraction of the payload total is managed by the company, which can charge a fee for a kilogram. Now, the initial fees were $1 million per kilogram, $1.4 million per kilogram. Now they've gone up to $2 million per kilogram, unfortunately. But it depends on how successful those will be. Okay, so there is a lot of action, and if you want to put something on one of those missions, the first date is 2026. Now, ASI is discussing with the NASA.
Let me ask you a question here. Shackleton crater is purely public, like is NASA, or it's the Shackleton crater is also very, because it's 21 kilometers diameter. So it's not, I don't see it here. So it's essentially probably only NASA, Artemis and things like that, or?
It could be, you know, Stavros, 10 years ago, the American venture capitals, the one who make investments in Silicon Valley and so on, they made a company called SEC, Shackleton Energy Company. So they claimed 10 years ago that they would get in the game, invest $20 billion, which is more or less the yearly budget of NASA, depending on the years. And they were very credible. I remember the NASA people listening to the talks by the Shackleton Energy Company with eyes wide open, because they had the money, of course. And then they started this for a couple of years, 3 years, and then they decided in 2011 that there was no market at the time, that the rest of the world was not investing in the moon, it was investing instead of Mars. So they dropped the effort. And they were right, meaning the missions, everything started again with Trump. After China did the missions, Chang'e 1, 2, 3, and 4, that guy decided that they had to race, they had to do plutonium, gave to DOE the charge of making plutonium, and they said, let's go back in the game. And he did, they made announcements of opportunities for several $1 million. Now, Artemis was already there, but was very slow. It picked up quite a bit with the Trump administration, and now there is an interest anyway by the new administration. So that will go, but they will go slowly with big rockets and big companies like SpaceX and Lockheed Martin. However, these are pathfinders, and there is a lot of money in this. There are already a few $1 billion ready to be assigned with the Eclipse and Prism missions until 2030. Okay, let's go more quickly now. So the evolution of the Eclipse commercial lunar payload services is the following. They want to survive the lunar night. They will need the RTGs for that. They will increase mass and volume. Yes, they're making landers which are bigger and bigger. I've seen Intuitive Machines 1, 2, and 3, and they are bigger now. Mobility services, yes, they have rovers. In our mission in 2024, there are 5 rovers. And in IM2, early 23, there is a rover and a hopper. And then they also want to address the operation in the PSRs, permanently shadowed regions. Now, for that, probably they will do robotic missions with Eclipse. also as a precursor for astronauts in the Artemis program to go to the PSRs. It's very dangerous to go there. They have a problem with this, with the spacesuits. The spacesuits are late. So the whole Artemis program now is late by at least 1 year because only of the spacesuits. Because only of that. And the total delay is not final. So the Eclipse missions are very useful because they do science and exploration while we wait for the big things like the big rockets and etc. Now, this is a slide. Now there are a few slides stolen from Stavros because I want to show what we can do to support this proposal. This is a specific slide for a proposal that Stavros did to ESA. Philippe Lognonet there is the reference person for this seismometry. They're very good, of course, in Paris, in France. They are providing the big seismometer for the InSight mission. There's a long tradition there. Philippe is working with many people very well on this front. And then we work on the supporting the idea with reflectors. Now the baseline of the latest study that Stavros is leading is 3 kilometers. So this is an older picture. You see that the proposing team is quite large, and there are groups in several countries. There is strong French collaboration. In Italy, there are other people, and then UK, Germany. So this list hopefully will increase as we improve and evolve the instruments to do the kind of physics you do on the moon. Well, the kind of physics you do on the ground, to see how we can translate that, optimize that, do a pathfinder on the moon. So this is one of the basic ideas. So if you want to ask questions about some of the numbers and their physics reach, of course, you have to ask Stavros. I'm getting into the field now, and I'm working supporting Stavros for the instrument, which is a laser. So there is a lander which will land a central station, including the laser, and it's very schematic. You know that you need to have a lot of things there. But the basic idea for what concerns the reflectors is that 3 kilometers away, there will be a mirror. This mirror will be a reflector. We will align it, point it to the laser within a degree of accuracy, which is far good enough. There will be a reflector of 10 centimeter diameter. Now, our idea is to have 2 reflectors. One, so a double system, one pointing to the laser, to the local lunar laser, the other one pointing to Earth. So we can do both gravitational wave physics and the weak field slow motion physics in the way I showed you before. Now, the additional advantage is that it will be a redundant system. So suppose that one of the 2 reflectors fails for some reason. Then we can rotate the system rigidly and use the second reflector for the most important science, which is gravitational wave. If we do a pathfinder for gravitational waves, then of course that's the priority, and that's also redundancy. Okay. No, it's a retroreflector. It's a retroreflector, yes. Otherwise, you have to mount your castle, do the usual job in the moon, on the moon, which is too much to ask for at this moment. So the reflector, it will inherit from what we're doing. The reflector will sit on a lander. It can sit on a rover. It's a robust system. And we are doing what we need, the basic tools, which is the pointing actuator and the dust protection. Because of course, if that is deployed by a rover, while the rover goes along the way over 3 kilometers, it will raise a lot of dust. So you don't want to go there and have all your eyeglasses completely dusted. So we need that. Now, what science we can do with our Moonlight reflector? Moonlight stands for Moon Laser Instrumentational for General Relativity and Geophysics High Accuracy Tests. Okay, so T stands for tests, H stands for high, and G stands for geophysics and gravity. Now, doing such an experiment for gravitational waves on the moon, it means you have to measure also the seismic activity. Okay, so you need to have a seismometer. So in this picture, you have to imagine that you have, in addition to the reflector, also there a seismometer made by the French group. So it will be an updated, evolved, adapted version of the seismometer on InSight, which works beautifully. And the two
Effect optical fiber 3D. It's a very
so
nice-
not exactly the one. It's not the same as on InSight on Mars.
No, it's not like the same. It is
Okay.
an extent. It can be the same,
But
an extension of the same, but they have now funds to make an optical seismometer with the fibers. Sagnac.
sure. The OVBB at the bottom there. Yes, absolutely. But the group has a strong experience in seismometers since a few decades, so that's a guarantee for the quality of the work. Now, so I don't want to go in other details, but with the reflectors on the moon, you do metrics, so you do the weak field slow motion physics, but you also do the good old surface geodesy. You put reference frames which help you define very accurately the local lunar reference frame, tie that to the international terrestrial reference frame because your stations are anchored on the tectonic plates of the Earth. And since you go there with missions, then you can put them together into the so-called international celestial reference frame. Now, it's not a game of acronyms. If you want to understand gravitational physics in solar system, you need to have a common reference frame and then ultimately refer everything to the solar system barycenter because we are following our star in space. So markers, fiducial markers, metric markers on the Earth are plenty. If you want to go to another planet, you need markers on the surface, and then you need the instruments which can give you information on the interior of the planet. Okay, so in order to study the geophysics of the moon, there is a very rich program. Some of these missions of Eclipse will bring seismometers. As Stavros mentioned, one is going to bring a seismometer, a French seismometer on the far side in 24-25. That is very important because it increases the lever arm of the measurements. And then there is a very big proposal in preparation since, I would say, a decade, which is called LGN, the Lunar Geophysical Network. The first proposal we did was in 2012. The PI is Clive Neal of the University of Notre Dame. The PM at that time for the discovery proposal in 2012 was Bruce Bannert, who is the PI of InSight. He made two proposals, Moon and Mars, and the one for the Moon called Lunette at that time was not approved. Now the next, and there was a proposal for a discovery mission, which is a mid-size at ESA, so $500 million. The next incarnation of the proposal will be a New Frontiers proposal, which is 1 billion, like the large class mission of ESA. And we are aiming at New Frontiers 5. It's being issued as we speak. Within a few months, there will be the official announcement of opportunity. Now, we are proposing seismometers, reflectors, 4 stations, 3 on the near side, 1 on the far side, with laser ranging measurements done from the French, Italian, and American station, and laser altimetry around the moon with either the current Lunar Reconnaissance Orbiter or the next Lunar Reconnaissance Orbiter, which is being prepared now. I mentioned before GRAIL, Gravity Recovery and Interior Laboratory. That is an orbiter. GRAIL was made by 2 orbiters, very similar to GRACE, which is a mission on the Earth, which is very low, with 2 satellites which track each other with a very high accuracy, with interferometric accuracy in the radio. And they, by measuring the perturbations between the baseline between the 2 satellites, people can measure the spherical harmonics much better to a very high degree. This was done very successfully on the Earth with GRACE A and GRACE B, and then both have laser reflectors. So you not only do this with the radio interferometry, but you also do this with 3D vectors with the laser ranging. Now, on the moon, there was Grail, and that provided a lot of information on the crust and the first layers underneath. Anyway, so our reflector will provide now here is an explanation of why we improve the accuracy with the single reflectors. So if you have an array of reflectors, you get many pulses. Sometimes you get only one pulse, and you don't know if it comes from the near corner or the far corner. So you have you see there the famous Gaussian with the width of 2 nanoseconds. Now, the bottom plot is done with a reflector put on the roof of the building in front of the laser station. So if they shoot the Apollo 15 reflector on the moon, they get the Gaussian. If they shoot a reflector between 100 meters, they get something more narrow. It's not a delta. It has a finite size. If you look at the number, it's 2 millimeters. And that is because if you're working with a Gaussian of 60 centimeters, there is no reason, to have electronics and detectors which make you 0.1 millimeter. Once we will have the new reflectors, which will have, which support an accuracy less than a millimeter, then there will be a reason for them to improve their electronics, to improve their detectors, and do better on a point which is on the roof of the building in front of them. So we need to replace or add new reflectors with the old ones. Now, the laser return of one 10 centimeter reflector is about half of the Apollo 11, okay, 50%. However, the laser return of the Apollo 11 is down by a factor of 10 because of dust. So our reflector will be brighter, significantly brighter. It will be protected from dust. So this advantage will be useful for many years. So there will be an immediate improvement, but then it's an improvement broken into steps, a factor of 10, and then to do the next factor of 10, you need the geophysics. Okay, so same picture. This is the optical quality of the reflector now. So 10 centimeter diameter, that's me with my iPhone taking the picture. The reflector flips by 180 degrees the picture, so I'm not upside down. It's the game of the reflector. It's a fused silica supersede 311. It is uncoated at the moment, because the coating in the back can be source of a thermal problem, because since it is an exposed optics, it sees the sun. So the glass is transparent to most of the solar constant, okay? But then it hits the aluminum, or it hits the coating in the back, or the silver, hits those 10 microns or a few microns of metal, so that hits the back of the reflector. So the front of the reflector instead is very emissive and it loses heat. So you end up having a gradient of temperature between the tip and the front. So a gradient of index of refraction. And so you may have, for lunar laser ranging, standard lunar laser ranging, a dispersion of your far-field diffraction pattern. If you have a gradient by a few degrees, 3-4 degrees, that's too much. It spoils your lunar laser ranging. Now, for local surface lunar laser ranging, this is less of a problem. So the coating could be conceived. Okay, but anyway, it's a source of thermal perturbation, certainly, because this is exposed optics. If you go to a PSR, perimeter shadow region, you don't see the sun ever. So in that case, it doesn't matter. And that's one of the options. Those two plots there show the so-called optical cross-section, the amount of laser return in standard units, which are a million of square meters. So if you use the green, you get a laser return at 4 microradians, which is above 200 meters square meters. If you use the infrared, then of course the cross-section is smaller, but both are usable. And from the point of view of surface lunar laser ranging, you have plenty of light. So this is an issue only if you do laser ranging from ground stations. Now, The diagonal angle offsets you see there, so the back faces have 90 degrees among them, but you can change that angle in order to model the diffraction pattern. You could increase, widen the diffraction pattern if you need it. So that's a typical accuracy that we need. But again, that is not so important for a short baseline laser ranging on the surface of the moon. So that's not a problem for gravitational waves. Now, this is an interesting slide. And with this, I've concluded. This is a risk analysis that Stavros requested for the reflector, for the seismometer, in order to understand which were the critical issues, their severity, and what were the solutions. So specifically for the reflector, at the moment, the optical quality is adequate for time of flight. So the total accuracy, the accuracy of the retroreflected wavefront after it hits one front surface, reflects the three back, and then also the thickness of the reflector, which can have a gradient of index of refraction. Let's not forget that. So that quality is wave over less than 10. Okay. So it's not a very good optical quality, but because we don't need it. Of course, it's a small object. If you ask Zeiss or another firm to make a better object, they do more polishing, they take more time, it takes more money, and then you can do it. So it's a very low risk. I mean, it must be done, but the cost of a single reflector is not very large. So it's of the order of 70K or even less. Okay. A mission to go a pathfinder would cost much more, so we can afford to spend more money there to get the optical quality which is needed. Now, the failure of one of the two reflector systems, or the failure of a reflector system of the point, or of the robotic cover, of course, is low, but it is non-zero. And if we have a double system, one used for gravitational waves with the local laser, one for the Earth lasers, then we have a redundancy. And if this low risk happens, then we can rotate the thing rigidly and use the other reflector. Just because the system by itself is not very expensive. Replacing another seismometer could be more difficult. Now, the contamination of the front face due to lunar dust is very low because it's a very slow process based on the experience of the Apollo reflectors. However, it's also very low because we will have an actuated mechanism which will protect the front face during the deployment, either by a hopper, a rover.
If I'm permitted a joke, with all these missions going on the moon, you will have people landing all over the place. So you will have.
That's also true.
Joke.
No, no, no.
They will not be.
You're joking, but in the beginning, so the risk will be very low. But if the agencies make a research station, or you remember the global village that the Director General of ESA, the previous one, wanted to build on the far side. The global village that Werner wanted to build, they did a lot of studies, no mission, but that was a real village with infrastructure, with the buildings made using 3D printing of the regolith. The regolith, that is not coarse. It's not sand like in our sea. It's a basaltic stone, which once you laser print it, is very, very compact, and it shields very well from the solar wind. If you are below half a meter of that, then you're safe. And it insulates thermally very, very much. Below half a meter of regolith, the thermal gradient is 1 degree. On the surface is 300 degrees. So it's not real dust or sand like we have it on the seashore. So anyway, future exploration may get busy. So it's not so much of a joke, at least for now. Now, the deployment, I understand that something which worries the agencies. If you say, I land with this complex system and then I want to go 3 kilometers away and deploy another complex system with the seismometer, the fiber, everything. Now, the technologies which are available are several. Of course, rovers. Agencies know where they can purchase a big rover, say from Lockheed Martin or JPL, but that big rover costs an enormous amount of money. So if you want to do a pathfinder and limit the cost, which is the exercise you and I did, but especially Philippe, you have to use small rovers or hoppers. Hoppers go fast. That's the idea. And it will be tested for the first time, as far as I know, with the Intuitive Machines 2 mission in early 2023 or very late 2022. The rovers are a consolidated technology. You just need to spend money putting on the rovers what you need. And then one good thing is that if you put a reflector on a hopper or rover, then you can range it, track it from the ground, from grass or from Matera or from Apache Point in the US, which is an important thing. Because then you know where you're putting the thing. In our case, we will have 2 reflectors, so we can test different also orientations of the vehicle, which will deploy the far station. Now, the final question that Stavros asked us, to me and to Philippe, was what is the risk of not arriving to TRL equal to 9 by 2028? In our case, I wrote negligible. Because we will have a heritage of the 2024 mission and other missions in the following years. Of course, when I say negligible, it means that I'm faithful or that we will prove that that mission will be successful. So we will know in 2024 if we are successful, and then by that time up to 2028, we can in fact say that the risk is negligible. So we will not have surprises, let's say. In a couple of years, we will know the answer, if this is really negligible or if we need to work more. But so this is one of the last slides. And here I put 2 papers which you found, Stavros. One is exactly this one about the hopper. So this is a paper made by people working on the hopper. And among those are also, so one is Intuitive Machines, the affiliation. So I know personally Martin, TD Martin, Mike Elke, several people at Intuitive Machines in Houston near NASA. So they are building this hopper. They go to Shackleton. Okay, so I didn't remember that. So they go to Shackleton. So you were right. Now, the Nova C, which I've seen in Houston, carries 3 core payload elements. The Prime 1, which is a drill. It's built in cooperation with Intuitive Machines, and it's something, it's a big arm which will flip and then do the prospecting, as they call it, of the volatiles. And then there is a communication network developed by Nokia. And then there is a mobile autonomous prospecting platform, the MAP rover by Lunar Outpost, which is the one on which we are putting an Italian micro-reflector. So the idea is that the rover will go slowly, we'll do several measurements along the way, a real exploration activity, and then the hopper, once it's ready, will hop and follow the rover. And in a couple of hops or 3, we'll reach the final destination and eventually may go inside the crater, but of course it will be dark. So they will do that, we'll try that at the end of the mission when they, of course, there is an end of life because this goes with the battery. And then if you are in the shadow or there is no more sun in the region, then everything stops working because there is no nuclear power on board.
There are 2. I've seen recently, there can be small rover, not expensive at all, with a camera or even a reflector, as you say, and just understand all the path. And then you have the hopper.
Yes, and then you have a hopper. Yes.
Yeah, that's great. So you don't have to have an expensive rover. You just a small rover that
understands
where things happen, and then
map is small. It's like this. I think it's even smaller. It's smaller than the Y2, written U2, YUTU deployed by the Chinese missions. Smaller than that, and it has antennas to deploy the network for Nokia. And then there is Micronova, the deployable hopper robot developed by Intuitive Machines. So this is happening, and of course it's not European hardware, fortunately. So if we want to make a proposal in Europe, that doesn't help very much. But you know, there could be a cooperation between Europe and the US. So this is certainly something to watch out for. Now, the other paper of yours which I took was this one of ShadowCam. I know personally Mark Robinson from the Arizona State University. He's the PI of the LROC, Lunar Reconnaissance Orbiter Camera, the very famous camera which made very beautiful pictures of the Apollo sites. So you can see the footsteps of the astronauts going from the lander to the rover to the ALSEP, the Apollo Lunar Surface Experiment, to deploy the reflector, to deploy the seismometer. Of course, the people who believe in conspiracies say that those were robots which left the footsteps. But and one of the things they did was to rediscover Lunar Code 1, the first rover by the Soviet Union, which had reflectors on it, which was supposedly observed with the laser by the Russians in 1972. They never had a laser, but they said they measured it once, and then they never found it again. It was in a place where it was supposed to be, in a box of 100 by 100 kilometers. So since the laser spot is 1 kilometer or 2, they tried, but they were never able to get it. When LROC by Mark Robinson actually made the picture, and they saw where it was within a spot of 10 by 10 kilometers, within a few days, they found it. So the number of reflectors went from 4 to 5 overnight. So Lunar Code 1 now is a new reflector which can be observed. Now, the perimeter shadowed regions, of course, they're not completely dark. There is a stray light reflected from nearby topographic objects like hills, the rim of the crater itself. So they made this camera for the Korean mission, for the Korean Aerospace Research Institute, and for the mission KPLO. Now, KPLO was supposed to have a laser altimeter, which was very good news, but then they had they couldn't do everything, and they decided to host the ShadowCam instead of a laser altimeter. So this is very interesting because it will look inside the perimeter shadowed regions and will tell the hoppers where to go to actually find ice, because we know from neutron measurements by the Russians that the hydrogenated regions inside the dark craters, they're not uniform. So probably there are regions in which the ice is clustered, even though it seems that some of those craters, deep 13 kilometers, are almost full to the rim of ice, because the ice is made by the solar wind, the alphas and the protons, which shower on those craters or on the surface of the moon for billions of years. Then the electrostatics is such that these ions drift to the poles, like this. And then when they go into a crater, the OH and H ions, they meet and they make ice. And over billions of years, they have almost filled some of the craters which are at the North and South Pole. So there is a lot of stuff to search. So missions will go there just for the search of water, life, not life, but that's experience you do.
I think the Indians too will try through the polarization of the reflected light again.
Yes, yes,
Yes,
you're right. And the Indian mission Chandrayaan-1 with the American payload M-Cube moon mineralogy mapper, they were able to measure the rate of formation of water on the surface of the moon. So what the picture I've done with my hands, the fact that solar wind showers and makes the ions and the ions move, they didn't do a film, but they did a measurement, a dynamic measurement with many passes where there is a spectrographic instrument, and they were able to measure these migrations and how much of these in matter of quantity happens every ton of regolith. So they can give you a number. What rate ice is made, is produced on the moon with this electrostatic mechanism, because that follows the terminator line. Terminator line, night and day on the moon, is very, very slow. So it's almost electrostatics. And the difference in potential between the two night and day is up to 18 kilovolts. So there is a lot of electrostatics, slow adiabatic electrostatics going on the surface of the moon. Anyway, so this is the end of the story. I showed you that, hopefully, I showed you that laser reflectors together with missions and all the rest, the laser stations, the laser orbiters, so it's not just the instruments, offer a rich science program. we are interested in gravity. Other people, other communities are interested in selenodesy, geophysics. Geophysics is needed to, study the fundamental gravity. A number of measurements are classic weak field slow motion, which is our field. I understand now that there is an interest in searching for gravitational waves with the moon because of their peculiar frequency range. And LSJ was a great idea that Stavros and others put forward. Reflectors can be useful. And the new imminent surface missions, after almost 15 years of orbital missions, open the way to a lot more activity on the surface. There are lots of funds. There is competition. The US is going because China was going. The Russians have partnered with China even before the war, working on surface infrastructure. Instead, the choice made by the US with Japan, Canada, and Europe was the Lunar Gateway, the Lunar Orbital Platform and Gateway, from which they want to launch the Artemis flights. So the Russians, the Chinese have more surface approach, direct to surface. Instead, the US and Artemis partners, they want to do that in steps and exploit a substantial resource in orbit, the Lunar Orbital Platform and Gateway to Mars. They also have in mind to use that as a gateway to Mars. So there is competition, there is a lot of money. And of course, doing gravitational waves on the surface of the moon is expensive, but there is money circulating, and it's the usual story of a bloodshed of proposals. If you have the resources, you have the manpower of people who want to work on that. That's the case. So that's it. I took a lot of your time. Sorry.
So, questions? Yeah. I would like afterwards probably just say, since you mentioned gravitational wave on the moons, what are currently, we had a workshop here. There are 3 proposals. One is Virgo, actually not Ego, it's Virgo in the moon. And that's from our colleague Karan Yani from LIGO, that proposes a sort of Virgo or LIGO on the moon. And then there are the other 2 proposals, one by Jan Harms, who wants a network of 4 optomechanical and cryo-mechanical, let's say, seismometers in kilometer are doing, the things that he's a big expert on. And the other solution, the other proposal, both him and the LSJ, as you mentioned, is to measure, use the moon as essentially the vibrating moon, use the normal modes. So you see the coupling with the understanding what is exactly the structure of the moon and what is exactly the surface. Both the surface properties and the deep structure are very important on both sides. So the other is to, exactly as you said, to use your strain meter, we can call it a strain meter, I mean the laser electron reflector, accompanied with a fiber optics that we also have deployed here, essentially a fiber, a laser, and coming back and become a multi-sensor detector that can understand with localized, essentially, what is called the lunar hum, because there is, a lot of noise in the low frequencies, talking about 1 millihertz and 1 hertz. First characterize that, and eventually, in the normal modes, you can have multiplication factors up to 10 to the 8th. If you use the model we have of the moon right now, there is a lady, Josipa Mastorovich, that made a very nice simulation of that. And the millihertz, between 1 millihertz and 20 millihertz, you have a multiplication factor of the displacements, let's say, by 10 to the 8th. Therefore, your detector should see it. Of course, as you go to the hertz, currently, I mean, Jan has made more or less a constant multiplication factor on 10⁶ as a first approximation. But we know that going to the hertz, the multiplication factor of the moon becomes 10,000 to 10,000. So it becomes a little bit more difficult. And then you have also more seismic hum the 0.1 the decihertz than what you have in the lower frequency. So we are playing with all these numbers these days to do that. But having exactly the LSJ proposal, you have the three. You have the seismometers, you have the laser reflectometer, and you have the fiber, and you hope that the association of the three takes you, I mean, it's the synergy of the three that gives you a sort of lower risk. Certainly measuring fantastic things about, as you said, geoscience, then also seeing what we can do with gravitational. It's a strain meter, it's a laser strain meter. But you see the very good things that you can see actually in Kagra or and there the moon, the seismicity of the moon is a factor of 1,000 less. Already you start with that. But would you need some kind of support or something? I don't know, anti-seismic support. Yeah.
Okay. Now, just to understand, the idea in your case is just to use one detector which is sensitive to gravitational waves, and the information of gravitational waves you extract by playing with the other auxiliary instrument to subtract.
It can be that you see directly, it is above the background.
If it is above the ground.
It can be at least in the middle.
No, can I add something? Since you are targeting low frequency of sensitivity or low frequency of gravitational waves, my first reaction should be you should target also the stochastic background, but you need two detectors at that point.
Exactly.
I understand that it's costly, but this could be the game.
That's why it is a pathfinder. If you manage to make it work, then immediately as you say, now we'll do another one in the antipodes. And then it is the ideas of Jan, etc. about
the idea of Jan in practice is
the old idea. I mean, when you wanted to measure the stochastic gravitational.
Yeah. While the detector, the other detector, I don't know about what LIGO is proposing. Probably it's a standard interferometer.
Yes, it's a standard interferometer. And people believe
the idea of Jan in practice is a review of the old idea of Joe Weber.
Exactly.
To use the modes,
exactly.
Use the moon as a resonant detector in practice.
It's a resonance detector. That's what it is. Also, there were a lot of things happening in Italy. Viviano, Fafone, you too, I think, if I remember correctly. You two were talking about these things.
This idea was presented. I saw this idea in 1976. We are old.
So do we have, and also here, and if someone from the people in Zoom, please also tell them to, please, people in Zoom, please express yourself. But first is Elena.
I had just a curiosity about how metric connects to all of this. What does metric?
Well, metric, we use the word metric to imply that we are measuring positions and distances in Cartesian coordinate systems.
Yeah, no, but the metric mission.
Oh, the metric mission.
The metric mission. No, sorry, I should have be more clear.
Yeah. The metric mission is an orbiting mission, Earth orbiting mission in low Earth orbits. The two PI and co-PI are Roberto Perron from IAPS, INAF IAPS in Rome, and Enrico Lorenzini in Padua. So the mission has three main objectives. One is to study, since it's a low satellite, to study the upper atmosphere, which is of interest for a lot of technical engineering missions for Earth observation, surveillance, etc. The other one is geodesy. And this is because they want to do a spherical satellite. Now, the satellite they want to do is not a replica of Lagios and Lares, fully passive point-like mass. They want to do a spherical satellite with accelerometers, with Galileo GPS receivers, an accelerometer in order to measure the one which is on Bepi Colombo, ISA, the Italian seismometer, etc. It's very useful when you have a satellite which is subject to known gravitational perturbations, like a solar pressure and thermal perturbations, meaning if you have one side of the satellite which is warm, it emits infrared photons, so it gives a kick on the other side. So if you want to make precise orbits, these non-gravitational perturbations are several. So one is the solar pressure, the other one is the Yarkovsky effect, this asymmetric heating of the satellite. The neutral drag due to molecules which are neutral, atoms are neutral, which heat the satellite when it's very low, and then the charged drag due to ions which heat so it's a measurement study of upper atmosphere, it's geodesy, and it's general relativity, because if you make a spherical satellite, you fill some of the surface with the reflectors, so we are in charge of that. And then you put other instruments like GPS receivers, possibly a VLBI, but then it's not more a spherical detector, and GPS, an accelerometer in order to measure the perturbations and subtract the perturbations. Now, Lagios and Lares are reflect spheres. They have fewer, smaller non-gravitational perturbations, but non-zero. So the limitation in the gravitational measurements is the non-gravitational perturbations. With metric, it's something in between. They want to do something in between and to do measurements useful also for atmospheric physics. So this is something which was proposed already a couple of years ago as a concept. It was never submitted as a mission to ASI. There was never a call for that. Now with the PNRR, with this new series of opportunities, it could be pursued. It could be pursued as a separate proposal. So it's led by INAF and Padua.
Okay. So, but it doesn't. It uses the Earth. It's
Yes.
not, it's
Nothing
not
to do with the moon.
Right. Okay.
And nothing to do with gravitational waves.
Okay. Yeah. No.
It's standard non-imaging science in orbit.
Yes.
Of course, NFN is proposing several detectors and potential emissions of astroparticle physics. And that's called non-imaging Earth missions. Some other initiatives are on space weather, monitoring the radiation, which is of interest for other reasons, but it's not, fundamental science.
Yeah, okay. Thanks.
Sorry, metric is a word which means
Yeah,
many
of
things.
course. Yes, yeah.
Okay. Other questions? If not, other.
If I am not wrong, probably I am wrong. In the slides just at the beginning, I have seen written all of retro reflectors. Am I wrong?
All reflectors.
I wonder if
Yes,
probably
we are working on that.
you are working on that. What
yes.
is the advantage of the all of retro reflector to the respect of the?
Now, I apologize. This picture, the picture of Lares on the radiation system was not supposed to be there. So behind that, you see the beautiful dome of Matera laser, and behind that, you see also the laser reflectors for lower probability. But where did you read the hollow reflector? Perhaps here. Yeah, there. Yes.
Not retro reflector. Sorry.
Reflector is, what is doing the retroreflection is the three back faces, which are 90 degrees. Now, one idea is that I remove all the glass, which makes mass, and which is a glass which is subject to thermal perturbation, so subject to the variation of the index of refraction, which spoils the optical performance. And I put there only the back faces. Okay, so on the back faces, it means you have to have an optical substrate like Zero Dur or something cheaper like Pyrex. So you make that thin, And then you coat that with, of course, a reflecting surface like a gold, aluminum, or silver. Then you put an overcoat protection. And so in principle, you can do a reflector, which is a cavo without the material. Now, this is less trivial than it seems. It seems a good idea because our reflector is 660 grams. If you only put the back faces, but if you make 3 separate faces, you have to make them very flat, and it's easy. You can coat them very easy once they're flat, but then you have to join them together. You have 3 choices: gluing, screwing, or silicate bonding, or a combination of them. Now, to do silicate bonding, which is very strong, you need the thickness. So you end up doing the back faces very thick. And the material can be not very light. So it's also very difficult to control the angle when you do the silicate bonding or the gluing. The accuracy you need for the moon is 0.2 arc seconds, which is, now 1 arc second is 4.5 microradians. So 0.2 is a very, very small angle. So when they do the silicate bonding, they can control the angle at 1 arc second, or even worse, 1.5. That's not good enough for laser ranging. You need half an arc second. So we did purchase those from US firm, which makes those for defense and militaries. They use it for, they called it to apply directed form of energy, so shooting something or someone. But they are optics which works in the atmosphere, where there are no large thermal gradients, or in closed satellites. They use it in optical circuits of planetary missions on Moon and Mars and Venus. They don't work at the moment. There is no hollow reflector solution which technically works in space as an exposed optics for more than a week. There were missions in the past, but they lasted a week, because then the accuracy is not enough, or it deforms elastically, so you lose the signal, or it deforms plastically, and then you throw it away.
I cannot directly machine it from a piece.
It turns out it's not that
Not
easy.
so easy.
You lose, it's not easy, especially not the single surface. You make 3 very good surfaces. It's the angle. You don't control the angle, and then when you go at the joint, of course, you don't do a sharp joint. You lose efficiency there, which is proportional to the area, so that's not too much of a problem. But the problem is the angle. So no one, but maybe the agency didn't invest enough money. Now we won a tender from ESA, in which they charged us with 2 industrial companies, one in France, one in Italy, to actually try and build reflectors which work as exposed optics in space. So the success is not guaranteed. It's an R&D. So
there must be nanotechnologies these days that start doing things like that. I don't know. It's a very even more naive question.
that could be a solution for small things. But the thing is, if you have a small aperture, then you have a very large diffraction. So they're passive objects, but you can play with diameter specifications quite a bit to do different things. So good catch.
So okay, it was a friendly talk. So we're really very happy to have had it, and it's now registered and for us to see again and we understand better. So thank you very much.